batches arrive at a rate of R times B, where B is the number of batches that we split or combined the jobs into. The jobs, in this case the batches, go to the first available processor and batches depart at a rate of R times B as long as the utilization is less than 100%. Utilization can be determined as follows: the arrival rate of R times B divided by the number of processors times the capacity per processor, or the arrival rate of the batches, R times B, times the processing time divided by the number of processors. In this case, make sure to use C, the capacity, for processing a batch rather than a job, because we have combined or split the job into batches. Let's also review the terminology used in different settings. The general term is that jobs, or perhaps orders, of one or more items arrive. In the Littlefield simulation, one job represents 60 kits. In the homework example, one assignment is 60 homework problems. Then we can split a job into multiple batches, or we can combine smaller jobs into bigger batches. In any case, the minimum size of a batch is of course one item. In Littlefield, these batches are called lots. And in the homework setting, we could, for example, split up the 60 problems into 5 batches of 12 problems. The lowest level is what we call items. In Littlefield, these are called kits, and in the homework example, these are called problems. We cannot split one item or one kit or one problem into smaller batches because that would be similar to splitting the atom. And again, recall that a batch always contains at least one item, but could actually contain multiple jobs or only a fraction of a job. So let's consider a worked out example where one assignment of 60 problems arrives every day. We have 5 processors, in this case 5 students, who can work on one batch each. So we're going to split up these 60 problems into batches of 12 problems, and each student will work on one batch of 12 problems. PS will then be the setup time, which is once per batch, and in this case, let's assume that's 3 minutes. PP is the pure processing time, which is once per item, and let's assume that's 2 minutes. The processing time for a batch is then the processing time for the setup plus the number of items in the batch times the processing time per item. The capacity for processing a batch is then 1 divided by P, where again, P is the process time for a batch, not just an item, and not the entire job. The total capacity for processing the batches is then, of course, the number of processors times the capacity of one processor. So in this particular example, if we split up the assignment of 60 problems into 5 batches of 12 problems, then the processing time per batch is 27 minutes. This means that each student will work for 27 minutes to complete the 12 problems. The total time that is being worked is then 135 minutes, but the throughput time is only 27 minutes because we split it up. The capacity is therefore 1 batch per 27 minutes, or 2.2 batches per hour, and the total capacity is 133 problems per hour. What if only one student were doing all of these problems in a batch of 60? Well, then there would only be one setup time of 3 minutes, followed by 60 times the 2 minutes per problem, for a total amount of time worked of 123 minutes, which is less than the total amount of time that is worked when we split it up into 5 batches, but the throughput time is now 123 minutes rather than 27 minutes. In other words, from the moment that this one student starts working on these problems, it will take over 2 hours to be done, whereas if we split it into 5 batches, it'll only take 27 minutes to be done. Finally, what happens when we have 30 problems from one course and 30 from another, and we have to have a setup time for each type of problem? Now we can, for example, work in batches of 6, such that each student will work on 6 problems for one course, followed by 6 problems of another course. Notice that each student is thus still working on 12 problems, but each student now has 2 setup times, once for the problems of the first course and once for the problems of the second course. The processing time for a batch is now 15 minutes, which means that each student will be working 30 minutes in total, which of course is 3 minutes more than before because of the double setup time. The capacity is 1 batch per 15 minutes, or 4 batches per hour, so in total we can work on 120 problems per hour. Finally, let's show you some graphs that really clearly show the impact of the batch size on utilization on the left and throughput time on the right. Notice that reducing the setup time allows us to reduce the batch size and still improve the throughput time. However, smaller batch sizes will increase the utilization, which is even more true if the setup time is longer. Thus, in summary, we notice on the left that as the batch size decreases, in other words, we have more batches, then the utilization will increase, and it will increase even more when the setup times are longer. And on the right, we notice that the throughput time first decreases as we split it up into smaller batches, but at some point will start to increase again because then there will be too many setup times. As such, we can identify the minimal throughput time, which for longer setup times will be at larger batch sizes. We hope that this video can help you solve some homework problems and give you a better grasp on what batching does to your throughput time and utilization. Thank you very much for watching, and join us again soon.